sodium thiocarbonate 4, which is the compound of interest here, has the molar mass of sodium thiocarbonate 4, which is 2 into 23 plus 12 plus 3 into 16, and this gives us 46 plus 12 plus 48, which is equal to 106 gram per mole. Here we are asked to look for the mass of sodium thiocarbonate 4 required for this. Number of moles equal to mass of substance all over molar mass. Since 0.1 molar is required, then it means that 0.1 mole is equivalent to 1 dm cube, which is equivalent to 1000 cm cube. Therefore, 0.1 mole is equivalent to 1000 cm cube. So what would be the volume of 500? What would be the number of mole for the volume of 500 cm cube? That will be x. To now calculate this x, we cross multiply. So x times 1000 equal to 0.1 times 500. So x, divide both sides by 1000. I'm going to have 0.1 times 500 over 1000. This cancels this cancels this. Then this becomes 0.5 divided by 10, which is now equals to 0.05 mole. This is the mole in 500 cm cube. Our interest is to look for the mass, and there is a formula that says that number of moles equal to mass of substance, mass of Na2CO3 all over molar mass. Number of moles from the question is 0.05 moles, which is equal to mass of substance. That is what we have to calculate over the molar mass. The molar mass is 106. In that regard, we cross multiply. So the mass will now be equals to 106 times 0.05, which is now equal to 5.3 grams. So the mass of sodium thiocarbonate involved is 5.3 grams. A molar solution of caustic soda is prepared by dissolving. How can a molar solution of caustic soda be prepared? A molar solution of caustic soda is by determining the molar mass of the caustic soda in 1 dm cube of the solution, or in 1000 grams of the solution. Therefore, the molar mass of sodium hydroxide is 23 plus 16 plus 1, which is 40 grams per mole. In order to now prepare the molar solution of caustic soda, we make use of 40 grams. We weigh 40 grams of sodium hydroxide and dissolve it in 1000 grams of solution. So the answer to this question is 40 grams of sodium hydroxide dissolved it in 1000 grams of solution. And if it is required in volume, then it will be 40 grams of sodium hydroxide dissolve it in 1000 cm³ of solution. So the answer to this question is 40 grams of sodium hydroxide dissolve it in 1000 grams of the solution. Identification of cations. This is the qualitative analysis where ions have different color of precipitates and behavior in excess sodium hydroxide. Zinc 2+ is the first ion here, which the color of the precipitate is white and is soluble in aqueous or sodium hydroxide. Lead 2 is also white in color and is also soluble in excess sodium hydroxide. Iron 2 is green in color and is insoluble in excess sodium hydroxide. Iron 3 is rusty brown in color and is insoluble in sodium hydroxide. Copper 2+ is blue in color and is insoluble in sodium hydroxide. Calcium 2+ is whitish in color and is insoluble in sodium hydroxide. Aluminium 3+ is white and is soluble in sodium hydroxide. From this table, it can be deduced that 4 ions have white color, but only 1 is insoluble in sodium hydroxide, which is calcium. So the remaining 3, which are zinc 2+, lead 2+, aluminum 3+, have white color and are soluble in sodium hydroxide. Other ions and their behavior in excess ammonium solution or in excess ammonia solution. We have zinc 2+. It's also white, so it retains its whitish color and is also soluble in aqueous ammonia. That is, it is soluble in sodium hydroxide and also soluble in ammonia solution with a white color. Lead 2+ is also has also white color, but it is insoluble in ammonia solution. That means lead 2 is white in both sodium hydroxide and ammonia, but the only difference is that it is soluble in sodium hydroxide and is insoluble in ammonia solution. Iron 2+ also retains its green color. It's also green in ammonia solution, but it is insoluble in ammonia solution. Iron 3 also retains its rusty brown color and is also insoluble in ammonia solution. Copper 2+ is also blue and is soluble in ammonia solution. Calcium 2+ has no precipitate. It forms no precipitate with ammonia solution. Aluminum 3+ is also whitish but is insoluble in ammonia solution. From this table, it can be deduced that 2 salts or 2 ions are soluble in ammonia solution. The first ion is zinc 2+, which is soluble and it is whitish in color. And also copper 2+, which is also soluble, but it has blue color. Identification of anions. How can anions be identified? Tests, observations, and inference. The tests for chloride ion. How to know whether a particular ion is a chloride ion. It is first added dilute HNO3 followed by silver nitrate. Then at the end you have ammonia solution. Why do we need to add dilute HNO3? We add dilute HNO3 to mask other chlorides from interfering with the system, so that the only chloride that will be precipitated will be chloride of metals such as silver. So the chloride here comes out as a white precipitate because of the fact that on addition of silver nitrate, it forms silver chloride, which is a white precipitate. And to confirm this, we had ammonia solution which dissolves the precipitate. So in ammonia solution, the precipitate dissolve. That is to confirm that it is chloride ion. Number 2, nitrate 5 ion. How can you confirm the presence of nitrate 5 ion? The simplest way of confirming the presence of nitrate 5 ion is by adding dilute HNO3 followed by a freshly prepared iron 2 sulfate, then addition of concentrated H2SO4.